All right, it's been a couple minutes, so let's go through these. The first thing that we want to check is that R of k is true for everything from 1 up to 4. So did anyone find that value? Oh, actually, this one we're given. We're given that a of 1 equals 4 in the problem statement. So for R of 2, did anyone find that one?
It's 5.
All right. And R of 3.
7.
Okay, and R of 4.
11.
And we found each of those just by plugging them into this first formula. So for example, 5 is 2 times 4 minus 3, which is going to be 8 minus 3, and that's how we got the 5. All right, and then we're going to do the same thing for R of n for the same values, just to check that they are equivalent. So for R of 1, we plug in 2 to the 1 minus 1 plus 3, which gives us 1 plus 3, and that equals 4. So that one matches. R of 2, did anyone find if that one matches as well?
Yeah, it's also 5.
R of 3,
7.
and R of 4.
11.
So we did find that all of those match up, and for each of those, just the same method that we've been using. For 5, you would plug it in 2 to the 2 minus 1 plus 3, which gives us 2 plus 3, and that gives us the 5. So are there any questions about how all those values came up? All right. So moving on, we're going to find R of 8 and R of 9. So I'll write those in. And we want to use either the recursive or the closed formula to find these, and one of them is a little bit easier than the other. Does anyone want to guess?
Closed, probably.
Yeah. So closed is easier because the recursive formula, you'd have to go back a few values. So we can just plug it right into the closed formula, and that gives us 2 to the 8 minus 1 plus 3, which is equal to 2 to the 7 plus 3. And did anyone find what that is?
131.
Yes, 131. And then we can do the same thing with R of 9, which is going to be 2 to the 9 minus 1 plus 3, which equals 2 to the 8 plus 3. And what did that one come out to?
$259.
Yep. 259. All right. So now for the last part of this, we're given that Amanda has already verified R of 8. So we already know that the closed formula equals the recursive formula for R of 8, and we're looking how to verify R of 9 without starting from the very beginning. So let's just write, we know that we're trying to find A of 9, and we can write A of 9 as 2A to the, or sub 9 minus 1 minus 3, which equals 2a to the 8 minus 3. And what's the next step here?
Plugging in 131 for a of 8.
So we know that it's 131 from our last part, and that gives us 262 minus 3, and that comes out to 259, which we know from part B that the closed formula came out to 259, so it's verified. Are there any questions on that problem? All right, let's keep moving on. So this is a problem by induction. We have a couple different examples of these because these are probably towards the harder side of the proof techniques. So I will let everyone work on that. I think I'm gonna give it, let's do 5 minutes. You probably won't get it completely done, but just get as far as you can. All right, that's about 5 minutes. So let's get into this proof. We're going to start with the problem statement. And it's always good to kind of know this outline before you get started to write it out. And that also makes it really clear with your work where your steps are. So for the problem statement, we want to explain what P of n is. And we're kind of given it this time. The problem statement that is already given is pretty much the problem statement that we want to use. So it's just a matter of writing it again, just to be really clear. So 2ak minus 1 minus 3, a1 equals 4 is equivalently described by an equals 2 to the n minus 1 plus 3. All right, and then we need to have a base case. And in this case, we weren't actually specified where n is, but we are going to find P of 1. Usually in your homework or quiz, that would be specific. So P of 1, let's start with the recursive formula, which we are given that a of 1 equals 4. And then for the closed one, we get 2 to the 1 minus 1 plus 3, which is equal to 1 plus 3, which is equal to 4. And we found that with that first problem that we did. All right, so now here's where a decision needs to be made, because you can go from P of n to P of n plus 1, or you can go from P of n minus 1 to P of n. There have been a few examples of each in lectures. So I'm going to let all of you pick. Just go ahead and put in the chat which one you'd rather see an example of, because I know sometimes if you see a lot of one side, it's easier to go from one to the other. Okay. So it looks like we're going to go from n to n plus 1. Is everyone okay with that? Okay. So if we start with P of n, we're just going to assume that P of n holds. And it's good to kind of write out what that means. So if P of n holds, that means A of k is equal to A of n. And we know that that substitution can be made. All right, so in the inductive step, now we're trying to show that P of n implies P of n plus 1. So does anyone know where to start with this? Do we want to start with the recursive formula or the closed formula?
You should start with the recursive.
Yeah. So we'll start by substituting n plus 1 in for k, which is going to be 2a to the n plus 1 minus 1 minus 3. And that gives us 2an minus 3. All right, what's the next step?
You plug in the closed formula for A of n.
Okay. So we can, because of the inductive hypothesis, we can make this substitution. And it's good to specify that this is by the inductive hypothesis. And then we can substitute in the 2 to the n minus 1 plus 3 minus 3. All right. And when you multiply this 2 in, that's going to give us 2 to the n minus 1 plus 6 minus 3. I'm going to move everything over here, running out of space. And that equals 2 to the n plus 3, which it's not apparent immediately. Oh, that's my cat meowing. Sorry about that. So for the closed formula, we know that it is 2 to the n minus 1 plus 3. And the since we started with the recursive with n plus 1, we're trying to get the closed with n plus 1. And you can see if we plug in n plus 1 in that closed formula, you end up with 2 to the n plus 3. So that has showed us that that is a to the n plus 1 as well, and it's true. Are there any questions on that proof?
When we were first introduced to inductive hypothesis, the hypothesis step, it would like do that a of like k plus 1 is equal to n plus 1, but then like later it's just like of the form a of k equals to a of n. So which is it really?
So there are two options when you're doing an inductive. You can either go from n to n plus 1 like we just did, or you could go from p of n minus 1 and imply that p of n is true. You
No,
can't.
I meant in like whenever you're writing the hypothesis step, they'll write that in this case they'd write a of k plus 1 is equal to a of n plus 1. But then in later lectures, they'd write that in the form of like a of k is equal to a of n. So I don't know which one to put for like quizzes or whatever.
So yeah, so if you're going from, I'm not sure when it would be in the inductive hypothesis to have a of k plus 1 equals a of n plus 1, because then the inductive step would need to be a of k plus 2. So do you know what lecture that was?
I think the first time it was introduced.
First time it was introduced. I'm going to make a note. And I'm going to go and look at that after this class and see if I can figure out what that example was. And then I'll make a post on Piazza if that was a mistake.
Okay.
But generally you're going either from n to n plus 1 or n minus 1 to n, because you have to increase the n for induction to work. And then there is a question. It doesn't matter which one of those that you use. Generally, one is easier than the other, but you can always do it either way, whichever one makes more sense to you. So we have another induction example later on today, and I'll do that one from n minus 1 to n to show that we can do it both ways. All right, did that clear that up, hopefully? Okay, any other questions on that proof? All right, let's move on to the pigeonhole principle. So I've highlighted a couple things here already, and that is because we're given, usually with the pigeonhole principle, we're given a few different numbers, and it's important to figure out which one is which, because we've got that m times n plus 1, and we want to fill in all the information that we know. So this 5 integers, can anyone tell me what that's telling us? What can we take from that?
That's what m times n plus 1 is equal to.
Yeah, can you tell us why?
Because it's how many items you have.
Mm-hmm. All right, and then is there another volunteer who wants to say what 2 would represent?
That would be m plus 1.
Yep, and why is that?
because that's like the least amount of objects you'll have in one container.
All right, so now that we've got that, you can do some algebra to figure out what M and N are, and those are both important to show before you start into the actual proof. So now that we've got a starting point, I'll let you work on that for another 5 minutes, and go ahead. Just about a minute more on this one. All right, let's get started on this proof. So the first thing that we need to figure out is what m and n are. So does anyone want to volunteer for what they got for those values?
M is 1 and n equals 4.
All right, and then is there someone else who wants to tell everyone one of those numbers is really important to us for the proof, and which one is that and why?
So n would be how many like buckets we need, so that would be important.
Yeah. So we know that we need to have 4 buckets or boxes or containers, whatever you want to call them. And so I always just like to draw 4 boxes visually. You're not required to draw boxes in your homework or in your quiz, but that just is sometimes helpful for visualizing. So we're given that we want to find 2 numbers that have a sum or difference divisible by 7. And that is going to tell us what we're going to label the boxes and how we're sorting these integers into them. So is there anyone who wants to volunteer what they labeled their boxes with?
Would it be like on the first, like, because we are adding and is the sum and the difference, so like the first one would be 0,
Mhm.
and then the next one would be 1 and 4, and then the next one would be 2 and 3, and the next one 5. Does that make sense?
You're really, really close. The only issue with doing 1 and 4, so 1 and 4 add up to 5, and eventually we want everything to be divisible by 7. So we want the addition of these 2 numbers to be equal to 7. So we would want it to be 1 and 6, 2 and 5, and 3 and 4. Does that make sense?
Yeah, that makes sense.
And then that will help us figure out our 2 cases. So the first case that we have is we can have 2 integers. Well, first of all, sorry, I skipped a step. We have to specify that by the pigeonhole principle, there will be at least 2 integers. Oops. There will be at least 2 integers in one box. And that's really important to mention because now in our 2 cases, we know that either the first case is that we will have 2 integers with the same remainder, or we'll have 2 integers with a remainder that adds up to 7. And oh, I skipped another step. Sorry, everyone. It's also good to specify up here that we're sorting them by their remainder after division by 7. So sort 5 integers by remainder after division by 7. So those 2 things are both important to have in your proof to explain why this works. Okay, now we really can move on. Sorry about that. So if we have 2 integers with the same remainder, then we can specify them as ki and kj, where ki is going to be 2 times some number plus the remainder, and k of j is going to equal 2b plus r. And usually we don't repeat variables in proofs, but why can we repeat that r?
Because the remainder should be the same in both of them.
So in this case, the best move usually, if you have the same remainder, is going to be to do subtraction and find the difference. So we have ki minus kj equals 2a plus r minus 2b plus r. And that gives us 2a plus r minus 2b minus r. And that means we can cancel out those two r's and just have 2a minus 2b, which is going to be equal to 2a minus b by factoring. And, oh, whoops, the 2 should not be there in like any of these. I don't know what I was thinking. Sorry, everyone. That should be a 7 everywhere. Because we know that these are all divisible by 7. So let's try that again. And then we can use closure down here. Okay, I kind of messed up on that one, but does everyone follow how it ended up? All right, so I'll move on to the second one, and this case will hopefully be a little bit more clear because I'll remember to do 7 instead of 2. So our other option with these boxes is that we have 2 integers with different remainders. But the key here is that those remainders will add up to 7. So we can say that ki is equal to 7a plus r, and kj is equal to 7b plus s. But what's the third property that we can use to do this proof? All right, so by the pigeonhole principle, because we know that they're going to add up to 7, we can say that r plus s equals 7. And it's important to specify that so that you can make the substitution later on. So now when we add ki and kj, we get 7a plus r plus 7b plus s. And if we rearrange, we can get 7a plus 7b plus r plus s. And then this is where we can make our substitution. 7a plus 7b plus 7. And now we're able to factor out a 7 to get a plus b plus 1. And again, we can use closure. And that gives us that the sum and the difference are divisible by 7. Well, the sum or the difference is going to be divisible by 7. And then also including a conclusion. Can someone give me a conclusion to write for this problem?
By both cases, there are 2 integers that are divisible by 7.
There are 2 integers with a sum or difference divisible by 7. Whoops, I don't know what.
I have a question. So where does the plus, like, what does the plus r mean? I know this might be very stupid, but.
So the plus r comes from the division theorem, where we know that to write, so if something is divisible by 7, you would write here, let me like make a little box over here. If something is divisible by 7, then you would write like a equals 7k, where k is some integer. But if something is not divisible by 7, then it's going to be 7k plus some remainder. So that r is just whatever is remaining. And that's why the pigeonhole principle applies here, because these boxes up here are sorted by their division after by the remainder after division by 7.
Okay, that makes sense. Thank you so much.
Are there any other questions on that one?
Can we do a homework problem?
I think we might have time, possibly, depending on how long this next induction proof takes, but I want to make sure that we get through all the problems that we've got on here first. Is that okay?
Okay.
So, oh wait, this one is by contrapositive. Would you rather go ahead and say in the chat or whatever, would you rather work on a contrapositive proof or an induction proof? All right. So, oh,
I think the contrapositive one can be finished quick, so we can just do that first and then do the induction.
so yeah, let's go through contrapositive really quick, just all together. So for contrapositive, let's start by just finding the contrapositive. Does anyone want to take a guess at what that is? Anyone we haven't heard from? Okay, so we'll go through it together. It's important to remember, so the contrapositive only applies to the implication. So it only applies to that section. We don't need to negate for all real numbers because it's not actually part of the implication. So the contrapositive is going to be, it's the inverse and the converse. So first we're going to switch the order and put this section at the front, and then we're also going to negate it. So if x equals 0 and y equals 0, then, and now we take this section and negate that as well. X squared plus y squared does equal 0. So now we can add them up together. X squared plus y squared equals, we are given that x equals 0 and y equals 0. So we get 0 squared plus 0 squared by substitution. And that gives us 0 plus 0, which equals 0. So that gives us that x squared plus y squared does equal 0. So since the contrapositive is true, then the original proposition must be true as well. All right. Any questions on that? That one's a little bit more of the simple contrapositives, but the biggest thing there is just knowing how to find the contrapositive. So are there any questions on that? All right, let's move on to that induction proof. This one is a little bit tricky because it's one of those ones with the summation. So let's start by finding our P of n. And you can definitely leave it in the summation form, but personally, I find it easier to write it as a recursive formula because that's essentially what this summation is giving us, is a recursive formula. Because for every single one of these, like as I increases, you're adding everything that came before it and then one more term onto it. So before my problem statement, I would usually put here, I'm just going to move this down. I would put let a of n equal and then rewrite the summation. Does anyone want to take a stab at how that would be rewritten? All right, so we can write it as a n minus 1 plus 2 to the n minus 1. Does that make sense how that translates? Okay, so I would also let b of n equal this other term. And that just makes it a little bit easier to distinguish between them as you're going through the problem. You're not by any means required to change it to that, but that's just a little trick that I learned to help me with induction. So now that we've declared those variables, our problem statement can be that a of n equals b of n for all n is greater than or equal to 1. So now we're looking at our base case. And we start with a of 1, which is going to equal 2 to the 1 minus this 1, which equals, and since we did from n to n plus 1 this time, we're going to go from n minus 1 to n for this problem. So our induction hypothesis is going to be assume that p of n minus 1 holds. And since this one, if you're assuming that p of n holds, you don't really need to do any of the algebra there because you already are given p of n, but it can be helpful to go through, if you're doing n minus 1 to n, to put the algebra here. So I usually will go through and say, that means we know that b of n minus 1 equals a of n minus 1, and b of n minus 1, let's see, I'm going to actually move it down. B of n minus 1 is going to equal 2 to the n minus 1 plus 1 minus n minus 1 minus 2, which is going to equal 2 to the n minus n plus 1 minus 2, which is 2 to the n minus n minus 1. Everyone still following on that?
Wait, now I'm confused because now you put p of n minus 1 in the hypothesis part.
Yeah, so you can do it either way. You can use p of n in the inductive hypothesis or p of n minus 1. But what's important is that if you've done one of those two methods, you need to go with the term after it. So if your inductive hypothesis is p of n, then your inductive step needs to be p of n plus 1. If your inductive hypothesis is p of n minus 1, then your inductive step needs to be p of n. The important thing is that you're going up a term from one to the other, because that's how induction works. You go all the way up to, you assume that up to this point works, and then you prove that the number right after that still holds. I'll put that in a little box and move it up here. Okay. Any other questions on why we can do n minus 1? Awesome. So now we're going to move into the inductive step. And now we're trying to show that p of n minus 1 implies p of n. So the reason that n minus 1 can work in this case is we can set that a of n equals, from our problem statement, a of n minus 1 plus 2 to the n minus 1. And we can make a substitution here. Can someone tell me what that substitution is going to be?
So you can plug in what you just saw for b of n minus 1 into where a of n minus 1.
Yep, we've got this term right here that is equal to b of n minus 1, and we also were told that b of n minus 1 equals a sub n minus 1. So now we can write in 2 to the n minus 1 plus 2 to the n minus 1 by the inductive hypothesis. And with some algebra here, we get that 2n plus 1 minus n minus 2 is equal to a sub n. And if we look back up at our problem statement, that is exactly what we were trying to show. We've got 2 of n plus 1 minus n minus 2, and that's what we found. So now we can say that a sub n equals b sub n, and we've proved it. Anyone have any questions on that algebra? All right. Well, we just made it to that time. Let's see, is it Suban? Is that how you pronounce your name?
No, but I did ask that question.
How do you pronounce your name?
Just call me Subi.
Subi? Okay. I know you had that homework question. I would recommend going to TA office hours and asking it, or you can stay after right now if you'd like.
I'll just stay after right now.
Okay, that works. Everybody else, if you don't have any questions, feel free to go and have a great day.
Thank you. Have a good one.
Okay, my question was number 11. I can just read it out. That'd probably be easier. Just
Okay.
do that because it's a simple one. It's use mathematical induction to prove that for all integers n greater than 2, 2 to the power of 3 times n minus 1 is not prime.
Is not prime. Okay. This one's,
minus 1 is below.
what was that?
The minus 1's not in the exponent.
Oh, thank you.
Yeah, it's outside.
All right. So this one is definitely really tricky. And the key is kind of like not necessarily obvious right off of the bat. It takes a little bit of working with the numbers. Did you plug in any values of n when you were working through
Yeah,
it?
I did P of 2 for the base case. Also, I meant to say that it's for all n greater than or equal to 2.
Okay. So let's plug in 2, which we get 2 to the 3 times 2 minus 1, which is 2 to the 6th minus 1. And what did that come out to?
63.
63. Okay. And just what are 2 factors of that?
I don't think there are any, right?
7 and 9.
7 and 9, yeah. All right, and then let's just plug in 4 times 2 minus 1 as well. And that is going to give 2 to the 8 minus 1. And what does that come out to?
That's not correct. It's 3 times n.
3, oh, yep. Sorry about that. 3 times 3, there we go. 2 to the 9 minus 1. Thank you.
It's 511.
Okay, and what are the factors of that?
I think there should be 7 and 73.
Okay, 7 and 73. And what you're going to notice as you keep going through these is that 7 keeps up appearing as a factor. And what we can take from that is that 2 to the 3n minus 1 is going to keep being divisible by 7, which by definition means that it's not prime. So I would recommend maybe changing the problem statement a little bit. So instead of just saying not prime, which is a little bit hard to prove, trying to say that it is divisible by 7, because that's something more concrete that you can work towards in your proof. Does that make sense?
But it says to use induction.
So you can still use induction, but just when you're writing, you've got, you write problem statement, base case. So in your problem statement, instead of having your problem statement be 2, why is my pen not working all of a sudden? Okay, well, I'm not sure why that's not working. So I'll just try and do it verbally. So 2 to the 3n minus 1, instead of saying that that is not prime as your problem statement, you can say that it's divisible by 7 as your problem statement. And you can still use induction from there, but you just have a different starting point. It's still
Okay.
technically the same, but it's a little bit easier to prove.
Okay.
Okay, and then again, yeah, feel free to come to office hours if you have any more questions on that.
Thank you. Okay, I'm gonna mute because there is construction happening in my apartment.